So our next speaker is Dr. Jim Watkins of Cornell University.
Thanks, Kimberly. Thank you all for coming. I'm a research scientist at the Cornell Biological Field Station on United Lake, but we do considerable work on the Great Lakes. I'd like to acknowledge Marge Rudston, my mentor there, and Kristen Hollick, who has led the nearshore biomonitoring program for several years now, and also Taylor Brown at Cornell, who's been working on the coregonid end with looking at spawning, she talked yesterday, and mostly focused on physical factors, and that we started working together to try to figure out how we can entangle the biological factors. So since Lake Ontario is such a large lake, being at Shackleton, we have very small vessels, so we really rely on the collaboration with many other binational groups, including the Canadian Lemnos Coast Guard boat, and also the Kehoe. These boats are so large that sometimes we forget about sampling near shore, and so there's other programs devoted to that, using much smaller boats and collaborations across the different agencies. But I'm going to try to tie those two programs together so we get a feel for overall zooplankton status in the lake in these trying times with questionable alewife and also attempt at restoring coregonids. So in this talk, zooplankton are incredibly important for early life stage recruitment of many fish, as well as being the important prey for adult planktivores such as alewife, coregonids, and yellow perch. Some of the data needs I want to address are the seasonality of zooplankton that we have. A lot of times we focus on summer as the main index, but I'm going to try to give you an appreciation for more temporal time periods. Also the spatial distribution, what I was talking about with the nearshore and the offshore. The overall abundance and biomass is very important, as well as there's a lot of potential. We do measurements of every taxa, so we have really good information on size distributions, which I'll show you some. And that's many fish kind of transition from smaller to larger zooplankton over time. And then the overall food quality, each item has different fat content and also is easier to catch sometimes. I'd like to kind of offer this, looking at some of the literature, the growth rate potential option, which it's kind of a bioenergetics base, so using a temperature field to evaluate fish growth, but also entwining a foraging model, so using light levels and overall zooplankton prey density to predict growth potential. I think this may be effective in the future. One thing that spurred this interest was going to Lake Huron meeting in Saginaw, Michigan, and Bo Bonnell and Lauren Eaton made this plot of kind of emergence of different fish species for larval. So we know that lake whitefish and cisco are incredibly early, soon after ice out, and but there are several other species that range the whole spectrum of time periods. But we know the incredible temperature changes, and also zooplankton availability varies quite a bit. So I'm going to break zooplankton down into just major groups for this talk. So we have cyclopoid copepods, which are used the yellow code. And Lake Ontario is actually kind of unique in having a strong cyclopoid community relative to other Great Lakes. The cowboy copepods that we use blue generally. There's a pretty large species, the Lumnicalis, which tends to be very deep, and that's up to 2.5 millimeters. But there are several other smaller diaphragmids. And then the cladocerans in red or pink are the kind of main grazers of phytoplankton, and they're incredibly good food source. There's also very small stuff, which sometimes gets missed. So it's really important to use small mesh nets, like 64 micron. And these include a whole range of organisms, such as rovers, copepod nauplii, which are known good food for fish larvae, and also the newly Dreissena velodur larvae. So a benthic species emits a lot of larvae, which has, like you would think, because it's a calcite shell, that it might not be such a good food source, but more and more it's becoming more and more found in diets. Looking at the long-term biomonitoring data for nearshore at this time, So the species actually, I'm using those color codes, but the boxes are actually working their way up. But you see this major decline in the late 1990s. That's really related to a lot of the nutrient declines, as well as phytoplankton declines, and maybe even mussel introductions. But it's a very definitive decline in nearshore populations. And through 2018, and particularly a big loss of Daphnia and osminids, and even Malpli are also one of those. I've worked mostly on the offshore sampling of all 5 Great Lakes. So looking at the EPA time series, which we are part of, you see much more. These are 0 to 100 meter tows, and there's 8 along the axis of Lake Ontario. You see pretty consistent biomass over time, but definitely a community change around 2004. And what you see is the loss of the yellow and the reds, and much more blues. So that's a switch from cyclopoids and cladocerans to calanoids. Now, if we look at Lake Huron, we have a nice package of data from all 5 Great Lakes. We see this is what happened in Lake Huron that caused such a worry. These are based on 11 offshore stations. Again, it's August offshore biomass. But you see this sharp decline, and which is continued to this day, and very dominated by calanoid copepods, which is seen throughout the upper Great Lakes right now. We've been involved in something called the CSMI program, the Cooperative Science and Monitoring Initiative. It's a cycle, a 5-year cycle. So we just finished up Lake Ontario in 2018. We may use that as a framework for getting a lot more zooplankton data at this time. So again, Lake Ontario is a large lake, so we rely on a lot of collaborators. Just to give you a context for that year in 2018, these are the different sampling events that we did with large vessels. And this matches very well to the bi-weekly nearshore biomonitoring program. But you see, like typically we only do April and August, but the CSMI allows us to get many more samplings. Notice the incredible temperature changes over that period. So when you think of larval fish emergence again, they're dealing with very different temperature regimes, which can have really big implications in bioenergetics models. And then you also worry about at any particular time, big variation in temperature. So this is a good example of late May, which we were out on. And basically you're seeing the nearshore, it's called the thermal bar, where nearshore water is very warm relative to the inner core. And that's important for some larval species because they might take advantage of that higher production nearshore and as well as warmer temperatures. But it is very unpredictable. They can go through sudden changes. So this is the sampling approach for the offshore stations in black triangles, and then the green stations, which are the nearshore biomonitoring. You can see we really covered the lake well, and that's really due to binational collaboration and the use of large vessels. This year we really wanted to be involved in the larval fish efforts that Taylor led. So this is, again, she mentioned this yesterday, 1,000 or more than 1,000 larval fish tows. And we contributed some of these offshore stations, or many of those, I think. And so our main approach is doing vertical zooplankton tows using 64 micron and 153 micron. This is it coming out of the water. And then we also, for fish larvae for Lake Ontario, we use something called a Tucker trawl, which is much larger than the typical bongo nets. We're out in the middle of the lake. And then they also have a rosette system, which has considerable water quality measurements and profiles. And the nearshore data for 2018 shows a few things. Cyclopoids are, this is going from late April through end of September, which is very important. So cyclopoids were in early on, but then cowanoids were later, and Daphnia was later. There was Nauplii also in June. So a good seasonal aspect of what was happening in the nearshore. And then if we contrast that with offshore, these are set up in size distribution. So again, the yellow is cyclopoids, the blue is cowanoids. And you again see that cyclopoid emphasis early on in the season, and then the Daphnia definitely builds up later on. But you can really see the two main modes of the size distribution. We're dealing with very different organisms. And a lot of on the smaller scale, which is the 0 to 0.5, which we use the 64 micronuts, this provides some information on that. So the black is Tricenid veligers, the green is copepod nauplii, which is just maybe copepods, and then rotifers. You see some increase over time, definitely a lot of veligers at the end of the season, a lot of nauplii in June, which is consistent with what the nearshore sampling. So quickly, I'm just going to talk about this growth rate potential. So Jonah Withers, who talked yesterday about Atlantic salmon, worked on southern Lake Michigan, looking at the survival of alewife and yellow perch larvae. He did, using thermistor data throughout in 15 meters of water, he had a pretty good temperature field for the time period when alewife larvae were there. And he included the zooplankton nets just in the center of these at the same time period. So he had a feel of what prey items were there. He did diet, so he knew what they were eating. And the yellow perch particularly were eating a lot of Tricenid veligers and nauplii. So using that temperature field in a bioenergetics model, he made these plots for 2010 and 2011. So the warm colors indicate successful growth, and then the blue is places where you might not grow very well, or negative growth. So in this case, deep water, and he's using different prey items here. But at this point, it's kind of a constant 0.7 of maximum consumption. Now, if you add the actual prey density, you get a little bit different picture, a little less success. And then this is alewife, and then in yellow perch, you have very different success under that temperature field. Now, USGS has done a lot of diet work. I'm turning to adult alewife. So we know that they're planktivores, they're very important prey items. So again, cowanoids and cyclopoids are a big part of their prey items. And that was really done intensively in 2013. We used kind of a cool tool called a laser optical plankton counter along these transects in the offshore areas from west to east. And what it does is it actually, from north to south, you yo-yo this vehicle, a pretty large vehicle, to get fields of temperature, which you see the stratification going from deepening from west to east. And then these are actually the laser optical plankton counter, which quantifies particles. And we have daytime and nighttime. You see there's two different layers of zooplankton. And the bottom layer is near the thermocline, and that fades out as you work your way east. So these could have very important applications for comparing alewife, which tend to be in the epilimnion, versus coregonids, which might prey lower down. And we see spatial differences in that layer from west to east. Whereas at night, the zooplankton are coming up to the surface. And these are just averaging those profiles. So the red is temperature. You see the thermocline deepening towards the east. And then the black line is the daytime biomass in zooplankton. So you get really fine resolution down to half meter of zooplankton abundance. You can break it down into certain size groups even, so a lot of potential. And note that most of the zooplankton daytime biomass was at 8 to 10 degrees, so very different. So just in conclusion, the nearshore zooplankton have declined over time with a clear loss of cladostrum. And it looks like overall our time series suggests that the biomass has been maintained, But a lot of our closing net data suggests that there might have been some vertical redistribution with these daytime deep layers, as well as changing composition towards more calanoids. We really need to keep an eye on the Nauplii and Dreisena villigers because they are abundant and they represent an important prey item. And the seasonal and spatial data that we have is available to address recruitment success. And these really need to consider the life cycle timing of the different fish species. And we hope to use this growth rate potential analysis to really pinpoint success in different species with different prey items as well as prey abundance. And I'd really like to finish off by just acknowledging all of our zooplankton analysis analysts at Cornell Biological Field Station. They worked very hard on this, and we're really excited that we're actually caught up. We're doing 2019 samples right now in 2020, which is pretty admirable. And I'd really just finish off by acknowledging funding from the U.S. Great Lakes National Program Office, USGS, and through the CSU program, and also the New York State Lake Ontario Biomonitoring. Thank you very much.
Jim, you've got about 3 minutes for questions, if you want to.
Any questions? Sure.
So on the EPA long-term summer zooplankton data set, they seem to show that cladostrum biomass in Lake Ontario has been declining.
Mm-hmm.
But then in the CSMI one, I saw
Right.
a peak in the fall for cladostrum biomass. Do you think our biomass is really declining, or are they just shifting away from that summer sampling period?
Yeah, that is an excellent point. Because the August is selected because of peak temperatures, but we do see these cladostrums coming in a little later. So that's the advantage of the biweekly biomonitoring and also the CSMI efforts to really pin down. So, yeah, I think there has been a shift, but also maybe a decrease of, time period of when they would be available. And they are very important for as grazers and food sources. Yep.
Do you have any thoughts on the mechanism that's causing the community shift?
A lot of people think like water clarity has made a big difference, and also just lower production in general. So shift to deeper production where counterweights, which live generally deeper, could succeed more.